In this astropictionary math problem, we would like to calculate the nuclear fusion energy produced by the sun over the main sequence lifetime. Let's look at the pp fusion chain. We start out with 4 protons that ultimately fuse together to generate one helium-4 nucleus. Now the mass of 4 protons is higher than that of one helium-4 nucleus, and therefore we have a mass difference, and that mass difference is 4.59 times 10 to the minus 29th kilograms. The 4 protons weigh more than one helium-4 atom, and therefore we have a mass difference, which is a positive mass difference. And you can take a look at this YouTube video if you want to see the math. Now this mass difference is only 0.686% of the total initial mass. So we start out with 4 protons and we find out that total mass, and only 0.686% of it is going to be used into generating fusion energy. Now that's just for one reaction. We want to find out the energy released by the sun over its main sequence lifetime. Now we know the mass of the sun is 1.989 times 10 to the 30th kilograms, and of this mass, only 10% is available for fusion. So not all of it. You have the whole sun there, but not all of it is used in the core for fusion. The core is just a portion of the sun. So it's about 10% of the sun's mass. So we want to know the energy released by the sun over its main sequence lifetime. Well, to know the amount of energy released by nuclear fusion, we need to know how much mass is available for nuclear fusion. So we have the mass of the sun, but only 10% is in the core. It's only available for use in nuclear fusion. And of this core fraction, only 0.686%, or 0.00686, is going to be used in the generation of nuclear fusion. So we need to multiply these out. And if you're not sure how I came up with this 0.686%, you can see this YouTube video. Let's calculate this math. We need to put in 1.989 times 10 to the 30th, 1.989 EE30th in our Google calculator, and we want to multiply it by 10%, that's only available in the core, and then we want to multiply that by 0.00686, because only 0.686% of the mass is going to be used in nuclear fusion. And we end up with 1.36 times 10 to the 27th kilograms. 1.36 times 10 to the 27th kilograms. So now that's the amount of mass that's being used, that's available, and we want to multiply that by c squared so we can find out how much energy is going to be released. So we're going to take this 1.36 times 10 to the 27th kilograms, and we want to multiply it by the speed of light squared. So I have to hit multiply plus a parentheses, 299, 742, 458, and I need to square that. There's the squared, close parentheses, hit equals. We have 1.22, we have 5, 9 is greater than 5, that kicks the 5 up to a 6, which is greater than 5, which kicks the 2 up to a 3. 1.23 times 10 to the 44th is our end result. 1.23. Then we have to look at the units, because you not only have to look at the numbers, but you also have to look at the units to see if the units make sense. So we have 10 to the 44th as our result. Now we have kilograms here, and then we have meter squared. So I'm going to put that as a meter and a meter. which makes meters squared, and that's going to be divided by seconds squared. So you put the seconds squared there. Well, a kilogram meter per second squared is just a Newton. So we have a Newton meter, and that Newton meter is another name for joule. So we end up having a result of 1.23 times 10 to the 44th joules. Now this 10 to the 44th is quite excessive. That's a lot of energy that's being released by the sun or available to be released by the sun over its main sequence lifetime. And the units worked out to joules, so likely my math also worked out.